Good morning, good afternoon, or good evening. My name is Pascal Bru. I am the Global Sales Marketing Manager of Formule Action. Today, I'm very pleased to co-organize that webinar with Denise Kostov from BRC. This webinar is very interesting because we talk about evaluation of mean size in liquid dispersion by SMLS, or static multiply scattering. And I'm very proud and honored to have Denise with us today as a speaker. Denise is an expert, a worldwide expert in nanotechnology and nanoscience. He will deliver that talk today, and that's really, really interesting because having such expert with us today. In your WebEx GoToWebinar box, there is a question box, and you can ask any question at any time. We have someone dedicated to answer your questions in real time, so feel free to answer the questions at any time, and Matthias will answer your questions. Just a few words before Denis starts his talk. Denis Kolstov, as I said, is a worldwide expert in nanotechnology. He has a PhD from the Cambridge University. He is the founder of the company BRC, which is a consulting company in nanotechnology, and is also the chairman of the ISO TC229 Nanotechnology Committee. And yeah, again, thanks, Denis, for giving us the opportunity to be with us today. Just a few words about Formule Action. Formule Action is a scientific analysis company. We provide instruments to characterize emulsion, suspension, or form. And what is the mission statement of Formule Action? We want to value formulator work by providing smart instruments which directly characterize the final property of materials. So we have various technologies to characterize the emulsion, suspension, and form, instruments dedicated to the stability and shelf life, obviously the particle size in concentrated media, but also shear rheology, curing and drying time analyzer, gelation analyzer, and phase transition analyzer. And what is important at Formule Action is that all the technology that we offer do not require any sample preparation, which is very important for the formulator because you are spending days, weeks, months to make sure that all your components are in equilibrium. And then before to start an experiment, we prefer to analyze the sample as it is without sample preparation to make sure that we characterize the right property. And that's one of the benefits of the SMLS, but I will leave Denis to explain everything. An ISO document has been published recently on SMLS, and that's the purpose of the talk today. And I would like to thank Denis for attending to this webinar and giving us the opportunity to listen to your presentation. So Denis, the stage is yours. Thank you, Denis.
Thank you, Pascal. Real pleasure to be here. I'm going to just switch to my presentation. Can you see my presentation?
Yes, it's okay.
Excellent. Good morning, good afternoon, and good evening. I can see that there are a lot of members of the community from all different time zones. Thank you for being here. My name is Denis Koltsov, and first of all, I would like to say thank you for the organizers to put this webinar together. Formule Action have been extremely supportive of developing this method, this technique to measure particle size using single point measurement, SMLS. And I just wanted to compliment Formule Action, the entire team who supported us through this. But above all as well, I would like to also thank all the numerous experts from all the countries that we worked with to actually make this possible. As you know, standards cannot be made by one person or even two people. It has to be a collective effort, and it's a consensus effort. So we spent quite a bit of time trying to address all sorts of issues, from metrology to user perspective to regulators, in bringing this standard document to public. So today I will talk. So this is the summary. I will talk very briefly about various points. Please do leave your questions in the chat, and either Formule Action team or myself will address them. So basically, I will starts straight away to tell you what we achieved and then why we did that. Tell a little bit about SMLS. It looks like most people on this call will know about the SMLS and TurbiScan in particular, but I will just recap that. And then I will go into development of the actual standard method applicability, what it is related to, what samples you can use, etc. And then obviously validation. This was a serious question about how you validate any new method, and ISO it has its own approach to this. Then I will talk about the actual document and mention the instrument. So to start straight away from the final clause, what did we achieve? Well, we published a technical specification. For those who don't know what ISO documents are, these are basically pieces of paper with instructions on them. There are instructions in terms of terminology, how you measure things, how you qualify your instrument, how you conduct the measurement. And all of these instructions have to be so clear that even when you translate it into Chinese or Spanish, they still have to make sense, and the results have to be the same. But above all, the actual technical content has to be agreed by a very large group of experts, and these experts they sit at the technical committee 229, which I chair. But I'm one of the few chairs that actually drafts standards as well. So I was leading this document for quite a few years, and with a great support of our experts from various countries. And Formula Action was really instrumental in bringing this forward. So in this year, in January, this document was published after quite a long process of development. So what does this document represent? It represents an agreement from all participants, that means the regulators, that means that industry, academia, and metrology labs, that this method actually makes sense in technical sense, but it also can be read and understood and not misinterpreted by all parties concerned. This means that it took a while to get the technical content agreed, and then the wording of it, etc., etc. So this was quite a long process. In preparation for this process, we obviously were asked to validate this method. You can't just trust somebody these days. You have to demonstrate that this method actually measures something with a certain uncertainty and certain limitations. So we conducted an interlaboratory comparison study, ILC, and I will talk about that also in a moment. So this document looks a bit like what it is on the side here. And interestingly enough, at the bottom of this document, you can see that there is an ISO and IEC logo. That means that it is also accepted by the IEC community as well. Why did we start talking about this? Well, quite some time ago, when myself and Pascal and others from the Formula Action team, we had this discussion. I said, look, there's a big problem in nanotechnology. In other areas probably too, but in nanotechnology, this was severe. What we had was that a lot of people were producing paints or products using powders or slurry type of materials, and they were constantly asked, what is the size of your particles? And as you know, the real substances they're a lot more complex than just a set of spherical beads floating in liquid. So normally what you get in a very dense solution is that these particles interact, they quite often aggregate, and they actually act as large lumps of material. And in fact, they don't act as nanomaterials whatsoever. So the regulators were asking this question. But when you give your solution to an analytical lab, they would put it in another machines such as DLS, particle tracking analysis, or others, and they would have to dilute that solution quite severely. So if you start with a paint or some sort of cosmetics formulation, you would actually have to dilute severely your sample. That in turn breaks down all these agglomerates and aggregates, and what you get is a real mixture of all sorts of particles, primary particles, constituent particles, agglomerates and aggregates, and that sort of misrepresented the actual picture. In reality, you had completely different set of particles to what analytical labs would actually see. And with due respect, they did a very good job. They would produce a particle size distribution, but it wouldn't be a real one, because simply by diluting or sonication of your sample, you would change the actual particle size and interaction within your formulation. So the questions were asked all the time: do we actually have nanoparticles in our formulations, or do they still act as big lumps or big agglomerates? And the idea was to have a technique, have a method that would actually help us to understand the real samples without doing anything to them. So this particles PSD, well, it's a nice representation, but do we trust it? Is it fundamentally flawed? I would say yes. So so then we went. So then we went and analyzed what can be done, and there is obviously a very mature technology developed by Turbiscan, but it's been used only for, technically speaking, for measurement of concentration as a function of height or temp or time, to establish the stability of the actual formulation. So this little video shows you how this works, but on the left-hand side you have a cartoon that tells you that the scattering, the me-scattering of particles predicts that obviously for not very dense formulation, you would get a much bigger transmitted signal, and for a very concentrated dispersion, you would get backscattered reflection. So this is quite intuitive, and we knew that when we started that. But the question was, can we use that sort of effect to also measure particle size? And in this case, the answer was actually yes, but we need to understand a few other things about the actual dispersion. So I will talk about that in a little bit more detail once the cartoon finishes. So the plot of the concentration, as you can see, the green dots and the red dots, they sort of follow an intuitive approach where if you increase the phi, which is the volume fraction of your dispersed material, you basically kill off the transmission and increase the backscattered signal. So when you look at the effect of the scattering on the measurement of size, please don't get put off by these expressions of backscattered intensity and transmitted intensity. They're just for those who like it. Intuitively, what happens is that just like before, but in a different sort of mathematical way, transmitted intensity goes down quite significantly when you increase the size, and the backscattered intensity goes up quite significantly. It actually goes sort of up and down afterwards because of the me-scattering. So it's actually quite an interesting cartoon here. So the red line depicts this sort of rise and fall. So on the static plot there, this is the black line by backscattered intensity. So it climbs up first and then tails off down. This particular document looks at the particles between 1 and 100 nanometers. But we all know that this particular technique works up to micron sizes particles. So the only restriction here, we were developing this document in the nanotechnology committee, so it was restricted to this uprising of the curve, the black curve here in the bottom left corner, where the curve is sort of monotonically increasing upwards, so it doesn't curl backwards. So that was the one very important aspect. So when we started work on this, that was back in 2014. ISO TC229 did not have much of appreciation of this particular technique. People knew about Turbiscan being used for stability measurement, and it was making quite good progress in this area. But sizing, technically, it was possible. People knew that these formulae that I just showed could be applied for transmitted and reflected intensities, but it's never been really validated and used. So, as I said, this document was developed only for the nanoscale, but as I just described as well, it doesn't have a limitation at 100 nanometers. What we did, and this is a normal procedure for normative documents under ISO, that they require an inter-laboratory comparison study. So in 2018, we managed to organize a very nice, concise inter-laboratory study under the VAMAS project. So VAMAS is an international sort of organization, a bit like ISO, that only looks at inter-laboratory studies. So it says Versailles project on advanced materials and standards. So, for example, characterizing something like cellulose or graphene or calibrating your electron microscopes, this is where people come together and do this. They pretty much do it for free because it's very good for the community, and obviously they get mentioned in various important documents such as this one. And then we managed to make final edits in 2021, and because of the delay in all the publications in ISO because of COVID, we ended up rolling into 2022, and the document was published with 2 logos, as I've mentioned. So this method is quite interesting from many angles, but we need to know certain things. So, for example, here we obviously need to know the volume fraction of the sample. If the volume fraction is not known, we may have an issue interpreting or calculating the data. It's also important to realize that because the volume fraction relates to concentration, if your sample is not uniformly dispersed along the vertical axis, so it's been sedimenting, for example, you may find that the measurement will not be that good. So there are some remedies in the particular document to actually take care of that, and obviously urge those people who want to have a representative size measurement to measure in a certain way. So there's a measurement halfway through, in sort of middle third of the sample volume. And we also need to know, obviously, the material that it's made from. Without this, we don't know the refractive index, and we can't do any calculations. What samples can we look at? Well, as if you've used Turbiscan, there's pretty much all of those samples, particles of many kinds, and then liquid droplets, emulsions, and also gas bubbles. So nanobubbles, for example, have been tried. And so these are quite interesting systems to look at. The density of the sample can vary from 0.0001% to 40%. So it's a pretty big range, in my view. Beyond 40, people have done this, but there are certain packing restrictions of how you pack the particles in denser materials, denser dispersions. That becomes a problem. For sizes, as I mentioned, technically speaking, this method can be used between 10 nanometers and 100 microns. So you have a huge range there. And what it can measure is those samples, we call them as received samples. So you don't need to do much at all. So just put it in a sample container and Bob's your uncle. In many other techniques, you would need to dilute, sonicate, or add some things to it. In this particular case, we don't. Obviously, if you want to run some sort of dilution experiments, that's not a problem. That particular document does not require you to do that, but you need to be aware that if your sample is not stable and it will sediment by the time you have stopped the measurement, you may have slightly misleading data. So you will have to sort of remedy that. But that's not because of the technique, that's because of your sample not being stable while measuring. Measurement is actually quite quick, as you know. It's a single point measurement. You can do several averaging runs, but single point measurements are usually quite quick. So talking about single measurement, this technique does not give you a full particle size distribution, of course. You only get a sort of aggregated answer for a mean particle size. We call it the equivalent mean particle size because it is equivalent to the mean scattering diameter of whatever particles you have. So if you have non-spherical particles, the system will also give you some sort of mean diameter, but it is for you to interpret that, because if they are elongated or in different format, then you might have to sort of interpret that data accordingly. And also, this method can be used for stability. So you can monitor the stability just at the same time as sizing. So once you know the volume fraction in any particular point, you can evaluate size, but at the same time you can run the up and down scanner and assess the stability independently. So this is two things in one. And obviously, in order for us to even present this to ISO community, a few fundamental questions were asked. How do you validate that? Well, first of all, we wanted to have a sort of nice and easy system, like, for example, in this case, 60 nanometer latex suspension in water, that for different volume fractions of our element, latex spheres, we would get sort of comparable results. And these are 60 nanometers, it's quite small. And we managed, so this was one of the first runs we had. So from volume fraction from 10 and going to 1 to 0.1, 0.01%, we obtained a relatively stable answer, because the spheres do not interact really. So this is within the error margin. Once we get a slightly more complicated system, in this particular case it's titanium dioxide in water, so we get different system, and this is a series dilution experiment. This plot here on the right shows you what the combined effective size of the particles was when we basically changed the volume fraction. And you can see the last dot is way up there, because this complex sort of particles, they sort of started agglomerating, and you can see that from some of the SEM images. They're not really scientific, it just gives you a perspective on what's happening at the nanoscale. They basically clump together if you put too many of them in the same volume. And so the last point at about 10% volume fraction was way off from the others. That sort of pushed forward the last bit of the actual validation was the VAMAS. So once we established we could measure the actual measure round, we run a VAMAS to not only evaluate the measurement itself, but also the measurement instructions. So those instructions given in the document, they're written, well, to the best of our knowledge, in the best way and best clearest way possible. But there's always a problem. There's always that PhD student who would misplace the sample and do it completely the opposite way. We know that. So our aim was to give it to a lot of laboratories, and we actually got 15 laboratories to work with us. And we, from 8 countries, you can see, and they were given 4 samples, sample A twice and sample B twice. And they were not given the size of those particles in those samples at all. So they were given the volume fraction, and they were given the material, which was the refractive index. And having those 2 bits of information, they used VAMAS methodology, which we developed, and they used TurbiScan, various models, and we have obtained quite interesting results. So for the smallest size, this is the sample A, 20 nanometer silica, but quite high volume fraction, we obtained a relatively stable set of data. This is actually not too bad for such a small size sample. Now, 20 nanometers is indeed really small. If you think about this, the techniques such as DLS and others, they can measure it, but they also feel that it's quite small, quite close to the limit of their measurement. So we didn't do too badly. So here our average, the red line, gave us about 15.8 nanometers. And so that was within the range of expected, so it's plus or minus 10% figure. Now, once we look at the sample B, which was 140 nanometer silica, but a lot less dense, we obtained quite a good measurement or mean measurement of the particle size, where we get less than 1% discrepancy with the mean, and that was quite nice thing to see. The document itself tells you that the size measurement can be better, but is usually within the range of up to 10% of the value. So if you put this in perspective, for example, DLS or PTA gives you plus or minus 5 or 10% as well. So this is actually quite in the same par as these techniques. So I was quite pleased to see that development. And obviously, this convinced not only myself, not only people who we worked with, but quite a lot of people who in the end read this document before publishing it at ISO level. They commented profusely. There were lots of comments, and we've spent a lot of time addressing all of them. And after that, it was published. And so the simple fact that we worked with so many people across the world trying to establish what is or isn't acceptable to claim in this document, what isn't or isn't acceptable to ask people to perform in this document. This is now a sort of consensus that this technique can do what it says it can. So the document itself has a title. So the number is 21357. I don't expect you to remember that. That's only ISO geeks like me who have to remember that. And the title is Nanotechnologies, like all of them. evaluation of mean size of nano objects in liquid dispersions by static multiple light scattering, SMLS. And then the scope, which tells you what it can and cannot do. This document provides guidance and requirements for the determination of the mean spherical equivalent diameter of nano objects, i.e. particles, droplets, or bubbles, dispersed in liquids using static multiple light scattering SMLS technique. The technique is applicable to a wide range of materials and does not require dilution of concentrated samples. On the right-hand side, you can see the standard sort of structure of this document. So there's the scope, normative references, terms and definitions, which are quite useful. And then it describes the principles, apparatus, measurement procedure, performance qualifications, which are quite important. And then the reporting format of the data and some of the measurement and so on. And as you can imagine, this technique is actually already installed in the instrumentation that is commercialized by Formel Action, and we have the Turbiscan a range of equipment, which was very well known for many years to do a very good job in terms of stability measurement. And now, in addition to that, you can look at the particle size. Now, once you have particle size as well as stability, you have quite a good handle on what is happening in your dispersion. You can also find the mean particle size, then maybe do something to your sample, for example, sonicate it or put a dispersant in it, or add another component into it, and then measure the particle size again. And then we'll give you a lot of quantitative information about what your samples do actually, because of all the procedures you're taking. So this is actually an interesting tool, and we are very glad to have worked with Formel Action team, who were pretty much instrumental in bringing this document together. And yeah, thank you for that. And just this is the last slide. I would like to thank everyone for your attention. If you have any questions, please ask the Formel Action team, or you can even reach me directly here at my email. And it's been a real pleasure to present this. So thank you.
Thank you, Denis, for the presentation. We got a couple of questions. So I could catch some questions during your presentation, Denis. You can either answer the questions or I can manage as well as you want. There were one interesting question, which was, can you measure mean particle size change over time with SMLS or that technology? Do you want to take it or take it?
Yes, definitely you can. As long as your volume fraction does not change. So that means that in a lot of samples, you get a volume fraction that may change with height. So you'll have some sedimentation or creaming. That means that where your laser is, there may be something basically getting thin. Your dispersion will get thinner. So if it is uniformly doing that across the whole sample, then yes, this measurement is actually quite interesting in terms of seeing the aggregation process happening.
Yeah, and without that, that's because we don't dilute the sample. We take the sample as it is, and we can repeat experiments over time. We can do acquisition every seconds, every minutes, so we can measure agglomeration rates with that technique as long as the concentration does not change. So when you don't have any sedimentation or creaming, you can definitively measure the agglomeration rate or coalescence rate if we are talking about emulsions. One more question, Denis, was about the refractive index. I think it was behind us. Can SMLS be used for diffusive materials? I guess behind that question was titanium dioxide or highly diffusive materials.
Highly diffusive material. Well, depends. There was never really limitation on this. Some materials do have high absorbance. So, for example, you put carbon nanotubes or graphene in there. But even those materials, I know some people have studied this. I've seen just at some conferences, I saw some presentations with people putting really thick black dispersion of graphene, and they've done this and they presented some results. They used Probiscan, they quoted that. So so it's been done. Again, if you go away from sort of spherical-ish particles, you will have to sort of interpret your data with a bit of pinch of salt, really, because you will have to sort of square a triangle or square a circle, because your answer will be a mean diameter. What's the mean diameter of a graphene sheet? So, but people have used other milky materials. Some of them are quite thick. Then you just don't look at transmission. You just get the backscattered data, and it's quite stable. As you can see, for example, from the from our measurements, we use backscattered.
Okay, thank you, Denis. And I think, as we said, I mean, all the measurement is driven also by the refractive index, and the higher the refractive index, or the difference between the continuous phase and the dispersed phase, the bigger is this difference.
Pascal, it's very faint. Can you speak louder?
Oh, sorry. I was saying that the more the difference of refractive index between the continuous phase, the liquid, and the dispersed phase, for instance, the particles, the bigger is this difference, the more sensitive is the SMLS, because we scatter a lot of light, so the backscattering measurement will be very high and very sensitive. So yes, definitely, as you showed you in your slide, titanium dioxide, for instance, which has a high refractive index of 2.5, depending on the material, works very well. Maybe the last question, Denis. Is there any correlation between the mean size you measured with SMLS and other size measurement done by diffraction technique, such as particle size analyzer or the particle size distribution? Is there any correlation or any number that correlate?
Yes, we actually tried to do that, but in the end, some of the connoisseurs of other techniques said, well, no, you shouldn't do that, because they felt that the scope of the document isn't to talk about other techniques, it was just to talk about SMLS. So we were a little bit upset because we actually wanted that comparison, but it was not to be. It's a give and take. So sometimes in these negotiations, you just have to say, okay, fine, indeed, the document was about that. Coming back to this, yes, there is some comparison, and comparisons are not too bad, actually. As you know, a lot of sizing techniques, they are basically technique dependent. So if you're measuring it with DLS, you will give a size and then it says DLS, because technically speaking, it's not going to be the same size as you would find in an electron microscope for the same material, because the equivalent diameter is completely different. So comparable equivalent diameters, for example, PTA and DLS, maybe. For SMLS, sort of similar situation, but it's somewhere between the hydrodynamic diameter and the actual SEM measurement. So they're somewhere in between, but they're not far off. I would say maybe 10–15% range, and so for these particle sizes, it's actually not too bad. So
okay, thank you, Denis, for the answer. I would like to thank everyone for attending to this webinar. Obviously, you have the email address of Denis, so you can contact Denis. You can either contact Formule Action at contact@formulaction.com if you have any questions. That webinar will be followed by a survey. So all the attendees, you will receive a survey. Feel free to answer that survey, and you will have all the contact details in that document as well, if you want to continue discussions with either Denis or the team at Formule Action to know more how the SMLS can solve your day-to-day challenges when you deal with nanomaterials and when they agglomerate, aggregate, etc., etc. So I would like to thank Denis again for your participation. Thanks everyone from either Americas, Europe, or Asia for attending that webinar. We have seen that we have people from all over the world today, so that was very exciting. And again, I'm Thanks everyone, and I'm closing that session. Thank you, Denis, and have a good day. Thank you. Bye-bye.
Thank you. Bye.